Okay, so hi everyone. Thanks for bearing with me with this. I'm going to try and quickly go over the material from today. So we are starting a new chapter. So this first section is on sequences. This is going to feel very different than what we've been doing. So we've been focusing on integration techniques and applications of integration. Now we're going to talk about sequences and series for a while, and then eventually in the end, we'll see some connection between those and integrals. But this is going to feel quite different. Anyway, so a sequence is just a sequence is an infinite list of numbers in order. Right? So it's just a list of numbers where we keep track of the order. And so how we would write this is if, say, our first term is A1 or A sub 1, A sub 2, A sub n, right? And then this keeps going, right? We could write it this way. So we just write out the list of numbers, right? So numbers in the sequence are called terms. And we usually write them A sub n, right? So read this A sub n, so sub for subscript. And this is the nth term, right? So the n refers to its location in the sequence. And then that number n is called the index of the term. Okay. So usually we will write the sequence if we have some formula for the nth term, we would write it this way, right? So the n equals 1 here, that's referring to where the index is starting. Usually it starts from 1 or 0, but it can start at other places as well, right? So this is our notation for a sequence, okay? And sometimes we just drop the n equals 1 in the infinity, so we could write it just like that. If you don't see an index, you can assume that it starts at 1. Okay, so let's look at some examples. So first we have this. Okay, so we have a list of numbers and we can see that there's some sort of pattern, and the dots just indicate that that pattern continues, right? So this is going to be doubling with each step, right? So my A sub 1 starts at 1, right? A sub 2 is 2, A sub 3 is 4, A sub 4 is 8, right? And so if we wanted to write this more compactly, we could find a formula for the nth term, and then we could just write it using that notation that we wrote down here, right? So what we can do is write 4 as 2 squared and 8 as 2 cubed. And then when I'm looking at this, what I want to do to find a formula for the nth term is look at how the index there relates to my term, right? So here for the index 3, the thing that's changing is the power on 2, right? And for my index 4, I get a power of 3. So in general, for the nth term, what I should get is 2 to the n minus 1, right? So check that when we plug in 1, that's 2 to the 0, and that is going to be the correct value for 1, right? Okay. So that means that we can also write this sequence as 2 to the n minus 1, starting from 1 to infinity. Okay. Another way that we could have written this sequence is we could have started from 0. So start our index at 0, and then our equation would be 2 to the n, right? Okay. So for our next example, we have this guy here, right? And we'll start from 0. And this exclamation point, if you haven't seen it before, is a factorial. So when we write n plus 1 with an exclamation point after that, that's the factorial. And what it means is we start from n plus 1, that number, and then we multiply it by every integer less than it all the way down to 1. So the next smallest integer would be n, right? If n plus 1, we started with an integer, and then n minus 1, and then we keep going all the way down until we hit 1. So we hit 2, and then 1, and then we stop. And we multiply all of those numbers together. So for example, 4 factorial is 4 times 3 times 2 times 1, right? So that's 24. Or another one to be aware of is that 0 factorial is equal to 1, and this is just by convention. So you'll just have to remember that that's the case. Okay, so what we have here is just our sequence is given in terms of that factorial, right? So if we start listing some terms at n equals 0, we get 1. At n equals 1, we get 1 over 2 factorial, so that's 1/2. And then 1 over 3 factorial would be this number, so 1/6, and so on. Okay, and then this next one is an interesting sequence that you might have heard of before. It is called the Fibonacci sequence. And it is defined recursively. So let's just write down the first several terms. So how we get started is we start with 0 and 1, and then to get the next term, we add those two previous terms together. So here I'll get a 1, and then the next term I add these two terms together, so that'll be 2, and then the two previous terms added together is 3, and then 5, and then 8, and then we keep going like that, right? So we say that this is defined recursively because the value of the nth term depends on the previous terms, right? So here, the how do I want to say this? The nth term is the sum of the previous two. So if we wanted to write down sort of like the recursive definition of this sequence, we would define the first two terms. So I'm going to call the first one A0 and the second one A1, right? So we had to start out with those two terms, and then we can say that the rest of them will be given by this formula. So it's the n minus 1th term plus the n minus 2 term, right? And that is the two previous terms, gives us the next one in the sequence, right? Okay, and this is for n greater than or equal to 2. Right? Okay, so this is the way we could define it. All right. So one way that we can visualize sequences is as functions, right? So, but they will be functions whose domain is the integers, the positive integers. Okay. So we call those the natural numbers. And that just means all of the positive integers. Right? And the notation that we sometimes use for that is this n with a double bar. You don't need to know this notation, but I don't know, in case you run across it, that's what that means. So what do we mean by visualizing them like this? For example, if we have the sequence 1 over n starting from 1, right? The way that we would draw this is, so if we have a function whose domain is just the natural numbers, then I'm just going to get one value at 1. So if this is 1 here, right? This sequence starts with a value of 1 at 1, and then a value of 1/2 at 2, and then 1/3, and then 1/4, and then we can keep going, right? So it just becomes this sequence of dots, right? And once we're looking at this, we can see, like for this sequence in particular, it looks like those values are going to keep getting closer and closer to 0. And it turns out that in the limit, as we push n to infinity, the limit of this sequence is going to be 0, right? So let's be precise about what we mean by a limit of a sequence. But basically, this is consistent with your idea of limits from before. So we say that a sequence a sub n converges to a number L, converges to L if we can make the terms of a sub n as close to L as we like, by making n sufficiently large. So by going far enough along in the sequence to get close to L, right? And so our notation for this is going to be the same limit notation, right? So we just express that as the limit as n goes to infinity of a sub n equals L. Or another possible way, but this is less common, that you can write this is that a sub n approaches L. So that arrow, you can read that as approaches or goes to L as n goes to infinity. So for example, how you would use that notation, you could write 1 over n converges or goes to 0 as n goes to infinity. Right? Okay. So yeah, we say that the sequence converges if the limit exists. We'll just give it a name. So we say this sequence converges if the limit exists and is finite. Otherwise, we say it diverges. Okay. And then diverging to infinity, what that means is that the values get as large as we like, or we can make the values as large as we like. So for example, if I have this sequence, so my a sub n is n squared, we'll start from 1, right? This diverges to infinity because the values keep getting larger and larger, right? So we can make n squared as large as we like by taking n to be large. Okay. Here is an example where the limit does not exist. For a sequence. And this is a pretty important example. So hopefully you will understand why this limit does not exist. Okay, so we have this sequence. We'll start from 1, going to infinity. So we've got -1 to the n, right? And if we write out the values in this sequence, right? So starting from 1, that gives us -1. When we plug in n equals 2 for the second term, we get -1 squared, which will make it positive, right? So positive. And then when we plug in 3, that will be negative again, -1, and then positive, and then negative, and so on, right? Okay. So when a sequence does this, we call it alternating. And what I mean by that is that, well, what I mean by when a sequence does this is that it alternates between positive and negative values, right? So this is because it alternates between positive and negative values. Okay, but we wanted to talk about whether the limit, or talk about the limit of this sequence. And I think it's helpful in this case to do that sort of visualization. So plot this on some axes, right? So starting, if this is -1 and this is 1, starting at n equals 1, we have a value of -1, right? Then 1, and then -1, and then 1, and then -1, and then we keep going like this, right? So we can see from this graph that this sequence is sort of moving up and down, right? It's never approaching a single value, right? It's always bouncing between -1 and 1. So it does not approach a single value. Which is what we would need in order for the limit to exist. So the limit as n goes to infinity of -1 to the n, oh, right, just does not exist. Okay. Okay, so when it comes to limits, all your familiar limit laws apply. Right. And if you can write, so let me say this more carefully, but if you have a function f of x that agrees with your sequence at every integer or positive integer, so the way that we can write that down is that when we plug in a positive integer n, that we get a sub n, right? So for each we'll say natural number n, then the limit as x goes to infinity of f of x equals L means that the limit as n goes to infinity of a sub n equals L, right? So, for example, if we are working with, say the limit as n goes to infinity of, let's see, n squared over 2 to the n, right? Then we would just choose our function to be x squared over 2 to the x, right? That definitely agrees with this. We just replace the n's with x's. And then in this case, we would just take the limit as we normally would. Now, this is a limit of the form infinity over infinity, right? So we can use L'Hopital's rule, right? We can just say, well, the limit as x goes to infinity of my function f of x is equal to, by L'Hopital's rule, 2x over the derivative of 2 to the x is natural log of 2 times 2 to the x. And then this is still a limit of the form infinity over infinity, but when we apply L'Hopital's rule one more time, we now just have a 2 in the numerator, and there's our denominator. We get 2 copies of natural log of 2. And now we get 2 over infinity, right? So this is going to have the denominator blowing up, so the limit goes to 0, right? Okay. And so we can conclude that the limit as n goes to infinity of this sequence is 0. And when you're actually showing your work, you don't have to write down the function and then compute the limit in terms of x. It's okay to just do everything in terms of n, but we're just being a little pedantic here because we're just introducing this idea. Okay. So the other thing that we should talk about is the squeeze theorem. So we have a squeeze theorem for sequences. And what this says is that if I have a sequence A sub n that is bounded between two sequences B sub n and C sub n for all n, then, oh, and the other important part is that these two sequences converge to some limit L, and they both converge to the same limit. So the limit of C sub n is also equal to L. Then we can conclude that the sequence A sub n converges and its limit is also L. Okay. So let's see an example of how this works, right? So here we've got n factorial over n to the n, right? So for this sequence, there's no way to write down a function that will match up with this sequence at each integer, each natural number, that is. because the n factorial, the way that we define it, doesn't make sense for non-integer values, right? So if we tried to plug in like even 1/2, right, that doesn't make sense in terms of the factorial. So what we'll need to do is something different, and turns out we can use the squeeze theorem. So first of all, notice, I guess let's just first notice that this is always going to be greater than or equal to 0. In fact, it's always greater than 0, right? Because the numerator and denominator are always positive. So what I'm going to do is just choose my one of my sequences to be 0 for all n. And then that definitely has a limit of 0, right? So that's going to be one of my choices of sequence. Now, to choose the other one, let's just write out a sub n, right? So I'm going to write it in a particular way. So it's n factorial over n to the n. And we know that n factorial is going to be n times n minus 1 times n minus 2, all the way down to 2 and 1, right? In fact, I'm going to write this slightly differently. So we'll just stop there, but we'll include maybe 3 times 2 times 1. Okay. There we go. And in the denominator, I have n to the power n. That means I'm going to take n and multiply it by itself n times, right? So notice that we've got n things in the numerator, right, when we wrote it out as a product. And for each of those, I can pair it up with an n in the denominator, right? Because we're going to have n copies of n here, right? So we just distribute them out like that. Now, what I can do here is pair up this product. So I'm going to split up the fraction because we have just a product in the numerator, product in the denominator. We can split these up. So I'm going to sort of pair these in this way, right? So write this as n over n times n minus 1 over n times all the other pieces that I get, like this, right? Okay. Now, when I'm looking at each of these, so starting at the first one, I've got this just simplifies to 1, right? And this guy, the next one, it doesn't simplify to 1. It's going to be something slightly smaller, right? Because we reduced the size of the numerator. So this is some number that's less than or equal to 1. It's actually strictly less than 1, right? And for each of these, like over here, 3 over n, that is also going to be less than or equal to 1. 2 over n is less than or equal to 1. And this 1 over n, we're going to leave alone, right? Okay, so if each of these pieces is less than or equal to 1, then I can say that when I multiply them together, I'll get something that is less than or equal to 1 times 1 times 1 times 1, all of these ones, and then I have my 1 over n, right? But 1 times itself, however many times, is just 1, so this is, so this just equals 1 over n, right? Okay, so what we've shown is that my a sub n, which is n factorial over n to the n, is less than or equal to 1 over n for all n, right? And so this is my choice for c sub n, right? That's what I'm going to choose c sub n to be. So we choose C sub n to be 1 over n, then we know that the limit of 1 over n is going to be 0 as n goes to infinity. So we get the limit of C sub n is 0. Also, the limit of B sub n, remember we chose that to just be 0 always. And so by the squeeze theorem, we can say that the limit as n goes to infinity of a sub n equals 0. Okay. So that is all I'm going to say for today. We'll be playing catch up, I think, a little bit, but this was sort of the necessary information from this section. We'll cover some more stuff tomorrow. And let me know if you have any questions about any of this. Okay, thanks. Bye.